Hello, students. We have a question out of the appendix. It deals with clock arithmetic or modular arithmetic. So what we're going to do is take a look at, first off, really understanding the big pieces. And this does go back to Math 105. So let me get a little bit of white space here to make sure that we understand the key ideas. All right. So when you are dealing with, does not matter what the concept is or where it's at, if you are dealing with addition, then we understand the concept of addition as we kind of add the pieces together, like objects add together. 2x's plus 3x's gives us 5x's, right? 2 negatives plus 3 negatives gives us 5 negatives. Concept is the same. Addition doesn't change. When we deal with subtraction, back in chapter 3, we got a chance to see that when we think about subtraction, we think A minus B equals C. What does this mean? What is it defined as? And so this is A minus B equals C if and only if A is equal to B plus C, and C is both unique and exists. Okay. So that means you can't have multiple answers to a subtraction problem. You have one answer. And unique means you can't have more than one. So this really beautiful balance between too many and too few, kind of like the Goldilocks story, if you will. Right? So when you see something that says subtraction, you can rewrite it and say, aha. So if I'm looking for subtraction, I could rewrite it as addition. And this is another definition of subtraction. In the book, this was known as the alternate definition of subtraction. A minus B is the same as A plus the opposite of B. All right. So now you have an operation. So if we had 3 minus -5, we could rewrite that as 3 becomes adding the opposite. And remember, when you do the opposite of -5 becomes +5. So that's the big picture. All right. So when you have clocks, right, you have options. You can keep subtraction the same and you have to think through subtraction the whole time, or you can find what is known as the additive inverse. And that's what this is. Additive inverse. Every number has one. So if you want to think about it, the number cloud plus what gets you to the additive identity. Now, the additive identity is the number that when you add it never changes. So to have an inverse is what you add to get back to what you started with. So typically we would, for these problems, write it as a negative symbol in front. Now we think of it as the opposite, but it's technically the additive inverse. So for example, if you had -3 plus what gets you to 0, the additive inverse would be 3. If you had the number 5, what would I add to get back to 0? The answer would be -5. So we have additive inverses. That same thing is true when we deal with clock arithmetic. So the concept of addition never changed, never. And all we're going to do is change the context. So now we're working with that clock arithmetic. So let's say that we're working with 3 minus 5. I'm going to put a circle around it so you think, no, I'm working on a clock. And let's say I'm working on a 12 clock. Okay, you can go and rewrite this, option 1. You can rewrite the 3 as something else that it's equivalent to on a 12 clock. For example, you could rewrite it as 15. Remember, just kind of adding 12s to get to the next one. And then when I subtract 5, that gives me 10. And since 10 is between 0 and 11, it works out fine. So there's my final answer. If you want to check yourself, then you would say 10 plus 5 is supposed to give me 3, and 10 plus 5 is 15, and 15 is equivalent to 3 in a mod 12 or a 12 clock situation. Excuse me. All right. So there's that. Now, what's the other approach? Instead of keeping subtraction and just changing the numbers, try to make it work out because that may take some more time for things that are not quick and easy. You could go over and say, well, let me replace this with something. Let me replace it with the additive identity. 5 plus what gets me to 0 in a 12 clock, right? So remember, 12 in a mod 12, 0 is like 12. So you can think of this as being like the number 12. So 5 plus what gets you to 0, or 5 plus what gets you to 12? And hopefully you'll be able to say, oh, I see it. 5 plus 7 is the same as 12, but 12 is the same as 0, so this works out. That means these two numbers are additive inverses. So when you have a problem like 3 minus 5, you can leave it as 3 minus 5, or you can rewrite it as 3 plus the additive inverse of 5, which we just saw was 7. And 3 plus 7 is 10. So that works out as well. Okay, so that's for addition and subtraction. I guess you could keep going. You could have even more ways. I know it's exciting. But what's another way you could do it? Well, if you had 3 take away 5, you could think about a 12 clock and rewrite the 5 to something that's equivalent to it, but negative. So go back 12 hours from 5 o'clock, and you will be at 7 going the other direction, right? Because 7 plus 5 is 12. So then you can think about 3 minus negative 7. Think about it back to the addition and subtraction you're used to, and that becomes 3 plus the opposite of negative 7, which would be positive 7. And that also gets you to 10. So a lot of options here. So many things you could be thinking about. I'll let you choose whichever way you like. This one with additive inverses is very, very helpful with multiplication. So let's take a look at that now. All right, multiplication. All right, what's the big difference between multiplication and what we just saw with addition? Not much. So if we had A times B equals C, that's the concept of multiplication. And we have a definition for what that is. If you go back in your textbook using sets, it's referred to as the Cartesian product, and that same definition can expand. It's not really the same as repeated addition, although the book mentions it does connect when you're dealing with whole numbers. I prefer to think of it as scaling up and scaling down. When you multiply by the number 1, nothing changes. If you multiply by something bigger than 1, it stretches it. It's like percent increase, and same going the other direction. So let's go over and try, how does that link to division? A divided by B equals C. So go back in your book. This is again chapter 3. If and only if A is equal to B times C, where C exists and is unique. So there you go. Once again, if you do a division problem, you cannot get 2 answers out of it. Okay. So if it looks like there is 2 answers, then you're going to have to say the answer is undefined because it does not match the definition. It would fail uniqueness if there's too many. It would fail existence if there is no solution. And in class, I mentioned this links back to something like 0 divided by 4. What is that equal to? Well, just come down to the definition. Well, that means 0 has to equal 4 times whatever you put in this cloud. Is there a unique number that you can put in there? Only one number that works to multiply by 4 and get 0. And hopefully you would say, yeah, there's only one. It's 0. So 0 divided by 4 is actually equal to 0. And you can check it. 0 times 4 gets you back to 0. Okay, what about something like 4 divided by 0? Well, again, let's just say that it equals some kind of cloud. That means 4 has to equal 0 times that cloud. Well, now let me ask you this. What happens when you multiply anything by 0? You multiply anything by 0, you get back to 0, not 4. So what this is saying is that there is no number that can go in here. No number, uh-oh, fails existence, which means we would say this is undefined, and it's because there are too few, aka no solution. But if you try something like 0 divided by 0, and I'm going to change the color so you can tell which 0 I'm referring to here. All right, let's see here. Then using this definition, 0 would have to equal the other 0 times the cloud right there. Okay, well, wait a minute. So what could I put into this cloud? Could I put the number 5? Mm, Let's check it. 5 times 0, that gives me 0, so it works. What about 25? Well, let's see here. 25 times 0, that gives me 0. So that works. So what numbers could you put in here? And the fact that 5 works and 25 works and -7 works and dot, 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 now we fail the uniqueness. So this 0 divided by 0, I'm sorry, this is undefined. And it's undefined because there are too many solutions. Now, why is that important when we deal with clocks? When we deal with clocks, we will see that it's possible to have things that look good, but actually do not work out. And so if you go to a 12 clock, on a 12 clock, if you were multiplying, right? Let's find multiples of 2. So let's see, we could have a 0, a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So there's all the possible numbers that I'm going to multiply by. I want multiples of 2. So first one, if I multiply, 2 times 0 is 0. 2 times 1 is 2. 4, 6, 8, 10. The next number would be 6 times 2, which would be 12. But if we're dealing with a 12 clock or a mod 12, we could also write that as 0. And then 7 times 2 would be 14. But again, in a 12 clock, that would be 2, 4, 6, 8, and 10. Now, why is this so important? Okay. So if we are saying something like, let's see here, 6 divided by 2, yes. So if I said, what is 6 divided by 2? You might immediately say, oh, well, that's 3. And you could say, but I'm going to prove it to you. 6 is equal to 2 times 3 on that clock. And I would say you're absolutely right. But 6 divided by 2 might also be something else. Notice the number 6 showing up here. Could also be the number 9. Let's check it. Is 6 equal to 2 times 9? Well, let's do a little math on the side. 2 times 9, that's 18. We are in a 12 clock, working mod 12, so we take off a group of 12. It leaves us with 6, and that checks out as well. Well, we've got a serious boondoggle here because now we have 2 numbers that are both working, or at least appear to work fine. So that means that this problem has too many solutions. So 6 divided by 2 is undefined because it has too many. Okay. Look in this table. Notice how you see 0, 2, 4, 6, 8, 0, 2, 4, 6, 8, 10. I don't see the number 3. So if I said, well, what is 3 divided by 2 in this table? And you said, I don't know. Let's put a cloud in for now. I need something that I multiply by 2, and I'm supposed to get back to the number 3. But look at all the multiples of 2. You never get 3. So this problem is actually undefined because there are too few. You could also say there is no solution. That would also be just fine. So when you're encountering these problems, there are a lot of different ways that you could go about doing it. When you're doing division, if you make a little table like this, like I just made right here, this is multiplication by 2. what you're looking at is all the multiples of 2. In order to be able to divide, you have to have the number 1 in that row of multiples. You need the number 1 because it is the identity element, the multiplicative identity. Okay, so let's go back and try this now with a different number. Okay, so I can't divide by 2 in a 12 clock. Nope, can't do it. It's not unique answer. Sorry. But let's say I want to do multiples of 5. So if I do multiples of 5, okay, it's a 12 clock still. So I put all these options down. Doo, 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 doo. All right, 0 times 5 is 5. 1 times 5 is 5. 2 times 5, oops. Oh my gosh. 0 times 5 is 0. 1 times 5 is 5. 2 times 5 is 10. 3 times 5, now I would write 15 down, but remember, this is a 12 clock. So we're going to work mod 12. So I do hit 15, but take off a group of 12, it gets you back to 3. 4 times 5 would be 20, but again, I take off a group of 12, and it leaves me with 8. So what you might be able to spot is you really are, multiples of 5 are acting like you're just adding 5 every time. So 8 times 5 would give me 13, but in a 12 clock, that would be a 1. And then you can add 5 again, 6, or you don't have to. You can multiply. 5 times 6 is 30. And take off a couple 12s, you get back to the number 6. So you can just keep adding 5, 11, keep going. Add another 5. What is that going to give me? 15 to 16, but take off a 12, be a 4. Add another 5. Add another 5, becomes 14. Take off the 12, becomes a 2. Add another 5, becomes a 7. So this is what's really cool is when you can divide by a number, every possible digit shows up in that row. There's a 2, a 3, a 7, a 6, a 5, a 1, exactly one time. And that's your huge hint. So that if I wanted to divide um, by something, right? Then we're looking for something I'd multiply by to get that number. So let's just say we're looking for the number 9, right? In this sense, you'd be given this problem. 9 divided by 5 is equal to what? Because you understand how division works, you turn it back into multiplication. You say, well, wait a minute. Maybe there's a multiple of 5 that'll get me to an output of 9. And it's right here. And so your answer is 9. So the answer to the division problem is 9. 9 times 5, you can check it. 9 times 5 is 45. I take off some 12s. So I take off, what, 36, because that's 3 12s. It leaves me with 9, and that is the answer I wanted. Okay. But if you were doing this division problem, then you would have to kind of have this table with you all the time. And mathematicians, like myself, don't find that to be particularly useful. So what we do instead is we say, let's take 9 divided by 5 and turn it into 9 times the reciprocal. Okay, so I got to go off to the side. 5 times what gets me to the number 1? Look in our table. 5 times what gets me to the number 1? 5 times 5 gets me to the number 1. So my reciprocal is actually the number 5. Now in a 12 clock, it's really cool. The number 5 is actually its own reciprocal. That's kind of nice. So you end up with 9 times 5. So there you go. So 9 divided by 5 turns out to be exactly the same as 9 times 5, which again you can do as your choice. You could think of it as being 45 and then take off a bunch of 12s. What else could you do? I guess you could think of the 9 as -3 and multiply by 5 to get -15 and then add a 12 and then add another 12 and you'll get back to your answer. So perfectly fine to think about it a couple different ways. All right, let's take a look back in the homework. And let's see what we got here. On a 12 clock, find each of the following: additive inverse, Additive. Okay, so these are additive inverses. Remember, that's the number I would add to get to 0. And then you have some negative numbers. That's fine. Don't treat negative numbers any different. You can just add the negative numbers together and then figure out what it is. That might actually be easier if you want to be honest. But that's completely up to you. So I've given a couple different techniques you could use here today. It says use the multiplication table to find 3 divided by 5 and 4 divided by 6. It did say the table in part A. Let's see here. In part A, which one is that? Oh, construct a multiplication table for a 7-hour clock. Okay, so you make a 7-hour clock, and then you do some multiplication or division with it. Okay. And that's all she wrote. So we should take a look at that. Okay, I hear you. Scott, help me make sure I'm on the right track with a 7 clock. Maybe I don't have a lot of experience with a 7 clock. Okay, so a 7 clock. Let's see here. What did it say? Divide by, was it 2 divided by 3? Okay, so I'm in a 7 clock. I need to find the inverse, multiplicative inverse. And what is the inverse of 3? So in my mind, because what I want to do is I want to rewrite this as 2 times the inverse of 3. So I need to do a little bit of work. I need to say 3 times what gets me to the number 1. So I need multiples of 3. Now this is a base 7 or a 7 clock. So here's my different values, and I'm going to find all the multiples of 3. 3 times 0 is 0. At least I got it right that time. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 would be 9. But we're dealing with a 7 clock, so I take that off and I get a 2. Okay. Times 3 again gives me 5. Let's see here. 3 again gives me a 1, and then this one gives me a 4. 3 times 6 is 18. I take away a couple sevens, I get 4. Aha! This is where you say, oh, I get it now. So 3 times 5 gives me the number 1. So 3 times 5 gives me the number 1. That means 3 and 5 are multiplicative inverses. If I'm dividing by 3, guess what? I can rewrite that as just being multiplied by 5. 2 times 5 is 10. Now remember, this is a 7 clock. In a 7 clock, that would be the same as 3 in a mod 7. So you can check it. 3 times 3 is 9, and 9 is the same as 2. 2 is what we were checking right up there. So there you go. What's great is if you found something to divide with 5, and you find the inverse, so the inverse of 5 is 3, the inverse of 3 is 5, I don't have to find another table with 5s. So if I want to do division by 5, let's just say somebody said, oh yeah, well, what is 6 divided by 5? And you can tell they're very angry about something. What is 6 divided by 5? You would say, well, that's okay. I don't need to stress out too much. I'm just going to repeat this. This is going to be 6 multiplied by the inverse of 5, and the inverse of 5 is 3. So that gets me 18, and 18 take off a 7, take off another 7, gives me 4. My final answer would be 4. And if you want to check it, you come down and say, well, wait a minute. You said 6 divided by 5 is 4? I said, yes. So what is 5 times 4? Well, 5 times 4 is 20. But take off a 12. What am I doing? 7 o'clock? Take off a 7. And that'll leave me with 13. Take off another 7. And that leaves me with 6. And that is exactly what I should get in my check. That is the connection between what we did with addition previously and what we're doing with addition, subtraction, multiplication, and division right now with the clocks. I hope that was helpful. If not, please let me know. I can do something different if you have a specific question. There you go. All right, that's it for now. Off you go.